Yeah, I was going to say. I'll just go right to and start asking questions because that's important. Okay, so Al asked me to come in and he said, talk about what you want. And this is what I came up with. Okay, so I've not given this talk before. I'm going to talk quickly. And, I think we want to get out of here in about an hour, maybe a little bit less. But if you have any questions, please ask them as I go along. All right. So in academia, there is no difference between academia and the real world. And in the real world, there is, right? And so I didn't intend this as a jab at academia, but I think it's, like most of this man's quotes, if you think about it, there's some real substance to what he's saying. And there's a real difference between the way that science is conducted, the way it's taught, the way it's implemented here in academia, and how it is carried out in industry, right? The important part here, though, is if that's not perceived, right? If academics can't perceive that this difference exists, well, then it would become almost impossible to convey that to students who then, right, move into industry. And so that's my point here. And so a big part of what I'm going to talk about in the context of offshore wind is how is it that we move from the left side over here, no pun intended, to the right side over here. And so this is a wind farm, right? This is what they look like. And this is one offshore of the UK, right? And this is a WTG, right? That's a wind turbine generator, okay? And this down here is a service vessel, I believe. So it gives you an idea of the scale. This is one wind farm, and there's a lot of them around the UK. This is another wind farm. This is offshore Denmark. One wind farm, but there's a lot of them around Denmark. This is Germany. One wind farm, but there's a lot of them around Germany, right? So here's just some quick statistics on wind farms. The UK has 39. Well, this is 2018, and these are fully operational, right? So not in any of the steps leading up to their commissioning. These are fully operational, putting power on the grid. 39 in the UK, 25 in Germany, and there's dozens of WTGs within each one of these. Denmark 14, then it falls off from there. This is U.S. offshore wind, all in, right? The whole shooting match right there, 5. Right, 5 turbines, you can count them on one hand. This is all the offshore wind power that we generate here in the United States, okay? In the background, this is Block Island. It's a very wealthy community. This island is offshore of sort of the border between Rhode Island and Massachusetts. And it was very unique circumstances that led to the construction of this wind farm, right? There's a very antiquated, I think I'm accurate when I say this, very antiquated coal-fired, or no, it was diesel fuel plant that they had there on the island that put power to the residencies there. It was an environmental nightmare. They couldn't get it re-permitted. They were ferrying over diesel from the mainland, and so this became a viable solution, and they built this wind farm. And then it stopped. I think this came online in 2016. So why? Why is this the case, right? I mean, the North Sea and the coast of the British Isles are littered with offshore wind farms, and here in the United States, we've got 5. Well, one is appropriate meteorological conditions, but we have those here in the States as well. But if you've been to the North Sea or if you've been to the British Isles, then you know the weather there, there's plenty of wind. So that's one reason. Land scarcity and land use, right? So I'm comparing the United States to Europe at this point in time. So people have been living in let's say, an agricultural or an industrial manner inside of Europe much longer than the United States. The land is, I don't want to say, let's say it's saturated from the point of development. It's not to say that there aren't green spaces and things like that, but there's not the kind of expansive territory that we have here in the States to develop onshore wind, right? Because we do have a robust onshore wind industry in the United States. We just don't have it offshore. So land scarcity, land use, that sort of covers that. Societal attitudes, right? So Europe, I spend a lot of time there. I'm painting with a broad brush, but I would say that they're more conscientious of green energy, of climate change. This is more in the forefront of their politics, more in the forefront of their table discussions. So they're more, I think, in alignment with renewable energies, and that takes us into the politics, right? So as you would hope, the societal viewpoint is reflected in their politics, okay? And the politicians there are willing to enact taxes and enforce subsidies, we're getting into the next part here, so as to enable these wind farms to exist, okay? So these are the main reasons why this is such a mature industry in Europe as compared to the United States, right? So the goal here, though, really for any alternative energy, but particularly wind, is to move into a position where they're in parity with conventional energy sources, right? And for the most part, this is fossil fuels, this is coal, this is hydrocarbon, these kinds of things. So this is an important, or rather imperfect but instructive exercise. So if you're an economist, take it easy. But if we start out at the same, if we start out at the same starting point here, right? Oil is a globally traded commodity, right? So more or less everybody's paying the same for a barrel of crude. There's refinement and there's different markets that they trade on, but we'll put that aside. But then you look and you see what, this was yesterday, it's gone up, but so $2.15 gallon of gas in the US. Germany, $5.65. Denmark, $6.44. UK, $6.10, right? So the point, and that's tax. That's the difference, right? That's the difference. A lot of tax. And so the point I'm making is in Europe, it is expensive, right, to burn hydrocarbon, to burn fossil fuels. The leverage that democratic governments have is through tax, right? They can incentivize people or de-incentivize people based on tax breaks and levying tax and things like that, okay? And this is important in the US, right, where we're a freer market, you could say, than most of Europe. And so how do they plan to get in parity with fossil fuels? And it's mostly through scale, right? Mostly through scale, and that's the scale of the WTG, right? Now they've made some advances in losses on the cables and the intricacies of the rotary system and the motors at the top, but the main thing is scale. And the airplane that you see superimposed there, that's an A380 Airbus, right? So that's a massive plane. It gives you a sense of how big these things are. And so this is, I'm sure there'll be a point where this will no longer be the case, but they continue to make these bigger and bigger and bigger, right? And as they get bigger, it actually works in favor of marine scientists because of the foundations. The foundations become more complex, they need to be better designed, and they need more information from marine scientist types. Okay, so as you might see, this is a story of why wind, that industry, is ascending here in the States, but it starts in Europe for sure, this story does. And so there's my previous slide. You add these things up, right? And you wind up with a viable offshore wind industry. This is Europe I'm talking about. You integrate that over time, you wind up with a mature industry, right? That's what they have. And a competitive market, right? It's very competitive over there. And you could say maybe saturated, at least from the viewpoint of some of the wind farm developers. So what do? Same thing that any business does. These are businesses, right? I think sometimes people get confused. Yes, it's green energy, and there's sort of a, I don't know what you would say, an air about that these aren't, capital-driven, hardline businesses, but they are. And so just like any other business, they come and they look for a frontier market, which is not typically the United States, but in this case, that's pretty attractive for them, right? So the US is the frontier market. We do have, it's not like they came over and thrust this upon us, this technology or idea. We are developing an increasing appetite for alternative energy in this country. And we have investment banks. And investment banks are key to this whole operation, whether it's Europe or whether it's the United States. These entire operations are driven by investment banks. Very different than the hydrocarbon model. And that's an important thing. Bear that in mind as I go through. Okay, so just to demonstrate the level of foreign involvement, in particular European involvement in this industry, these are the hotspots in the United States for development. And I'll explain later what these polygons are and all the rest of it, but I just want to make a point here. Right, so the blue one here, so this is Martha's Vineyard, Nantucket, so this is Al's neck of the woods, New England, Rhode Island's here, this is Jersey, this is New York City here. Right, so the red, these are blocks, right? So these are potential wind farms, right? These are areas that have been allocated by the state or the feds where you can develop wind. We'll get into that procedure in a minute. But the point here is the blue, that's deep water wind. They no longer exist. They were bought by Ørsted, right? Ørsted is a Danish company, so this is Danish. The brown one here, deep water wind, that's Danish. Bay State wind, which is this one here. That's Ørsted as well. That's Danish. The light yellow or whatever this is, that's Vineyard Wind, right? That is at least half owned by Copenhagen Infrastructure Project, so that's European as well. The pink one here, that's Equinor, right? Equinor is now the friendlier name of Statoil, right? Statoil is the state oil company of Norway, right? So you may or may not know, the United States is one of the few countries in the world that doesn't have state-run oil companies. Most countries, Democratic and otherwise, have state-run oil companies. That's their cash cow. Mexico has Pemex, Saudi Arabia has Saudi Aramco, Brazil has Petrobras. I could go down the list, right? So Equinor is formerly Statoil, right? Norway, believe it or not, I mean, you may or may not know this, heavy oil industry country. They make a lot of money in Norway, in the North Sea, off of oil and gas, and this is their state-run oil company. Ørsted, well, let me carry on with this. I can go on down the list. Equinor is this one is Mayflower, which is Shell, right? It's the closest thing to an American one so far. Vineyard Wind, again, half owned by the Europeans here. This is Jersey, this is all Ørsted, this is all Denmark. This block here, the blue ones are open. This part right here, this is Statoil, right, which again, that's Norwegian. And then down here, this one, the light gray, that's US Wind. Finally an American company, right? Nope, those guys are Italian. No shit, they're Italian. They called their company US Wind. Okay? What was I going to say? Oh, so these companies, Equinor, formerly Statoil, Royal Dutch Shell, they're an oil company for sure. Ørsted, they changed their name from Dong, which you can imagine why they did that, but that stood for Danish Oil Natural Gas, right? And that was their name for years and years. But so again, these are oil companies, right? These are oil companies developing wind for the most part, with the exception of the Italian outfit and then these Copenhagen infrastructure guys. Okay, so that's the story of the ascendancy of wind here in the United States. And now what's the relevance to marine scientists? Well, it's jobs, right? It's employment, it's career opportunities for marine scientists, right? So I won't touch anything here on the left, but 4 or 5 years ago, if you graduated from this institution or another one with a degree in marine science, any of the disciplines, this is what the job market landscape looked like. You had oil and gas, right? Very mature market, probably the pinnacle in terms of geoscience, at least in my experience. Pays the best, if that matters to you. Subsea communication, so these are the subsea cables, right? Heavily dependent upon marine scientists, particularly on the front end, but even through the installation, the laying of the cable, right? But you can imagine, you're going to, and there's lots of these cables. This is an industry right now that's booming, right? Laying fiber optic cable across the ocean basins. You can imagine that you would need a lot of input from marine scientists if you were even to know how long to make the cable, right? You can't just look here and here and say, we make it this long, right? I mean, plus the hazards and all the rest of it. Engineering, infrastructure, and environment, right? These are like construction jobs, you could think of this. This is any place where a construction or infrastructure project intersects the shoreline or the continental shelf. The most relevant around here would be beach nourishment, this kind of thing, harbor construction, dredging, right? These tend to pay the least. Offshore mining, this is, I think, a frontier market for sure. I think it definitely has a future, but I think right now, and I know Kevin can probably shake his head if I'm correct about this, they're able to explore, and these are the massive sulfides, if you're the black smokers, right, where due to the temperatures, pressures, and all the rest of it, there's precipitation of all kinds of metals and high-grade ores there. But I think the big problem is, how do you industrialize that process, right? I mean, how do you conduct an industrial mining operation in 2,000 meters of water and recover enough material, to make this a viable thing? I think that's the challenge in that industry. And then offshore wind, right? So before now, if you were a marine scientist and you were living in the United States and wanted to stay here, this would not have been a viable option, not at all, right? And now it is, and that's the relevancy. Okay, so bear with me on this. This is what I'm after here. I'm after the point at the bottom, is why you do something shapes how you do something, okay? For sure. And this extends to science, for sure. And so you can ask yourself, we'll start at the individual level here. Why is it that you do marine science? Right? Maybe a passion for the ocean, you feel like you're bettering the planet. Maybe it's ego-driven, a lot of science is ego-driven. Maybe it's the paycheck. And when I did this, I was looking and I said to myself, I said, look, that could be like a career path. You know, you start out passionate, then you feel like you're bettering the planet, then it's ego, and then at the end you're just getting a paycheck. So maybe there was some order to that. Okay, so this is, you know, any number of these things, or some combination, depending on where you are in your career. This is why you're doing marine science, or why I'm doing it. So we scale it up. We scale it up to the institutional level, right? So here's the vision of the College of Marine Science right here. So as best I can tell, this is why they do marine science here. I'm not going to read the whole thing in the interest of time, but the College of Marine Science seeks to increase and apply fundamental knowledge of global ocean systems and human-ocean interactions through research, graduate education, and community engagement. All right? So I know there might be some people from the USGS, just keeping it relevant to the audience. This is why the USGS does science. To provide science about the natural hazards that threaten lives and livelihoods, water, energy, minerals, and other natural resources we rely on, the health of our ecosystems and the environment, the impact of climate and land use, right? Now, why does industry do marine science? Painting with a broad brush here. Most of the time, there are some exceptions to this, but most of the time industry is doing marine science to decrease risk so as to reduce cost and to maximize profit, right? And all this centers around uncertainty and information, right? Marine scientists in industry are, for the most part, purveyors of information, right? This is an important thing. And that information is tied up in decreasing risk, right? So as to reduce cost and to maximize profit, right? So very different, that's my point here. Very different than the way science, very different reasons, very different application, very different methodology in industry compared to here. Right, so I want to talk just briefly here about the relationship between risk, uncertainty, and information, because it's probably not something that you think about as a student here studying marine science, right? So entropy, we should all be familiar with entropy. We can consider this the degree of disorder in a physical system, right? So the whole universe is moving towards a state of what the most disorganized form of energy is heat, right? So that's entropy in a thermodynamic sense. Now entropy in the context of information theory could be considered the degree of uncertainty. Okay, so that's entropy in that domain. And so mathematically, information is the reduction of uncertainty, or might be considered the negative of entropy in information theory. And if you want to see all the math behind it, this is the guy that did it, Claude Shannon. Okay? So I just said a lot about entropy and the rest of it just to come up with the conclusion that information reduces uncertainty. So that's about as no shit as it gets, right? But there's a catch, right? And there's actually two catches, and this is what they are. One is that the information must be relevant and it must be correct. And the next part is that information is not free. Okay? And so I'll borrow some statistical, I guess, nomenclature from the financial world because they think a lot about this, right? And so this distribution here, of course, this is the Gaussian distribution, could be any distribution. And of course, this is one of the main things is to figure out whatever phenomenon that you're investigating or look at, even if it's risk related, what is the distribution that best fits your data. But this will suffice for this conversation here. So this is the categorical forecast in finance, right? It is right here at the mean, okay? And the categorical forecast is something that we know will happen, right? We know will happen. And it happens at the mean, right? And as we move away from that, right, the mean, as we move away from the mean, we become less certain, right? And when we get out here into the tails of the distribution, right, this is where uncertainty lives, out here. And the fatter these tails, right, fatter these tails, the more uncertainty in this distribution, okay? And so as marine scientists, what our job is to move from this kind of distribution, or worse yet, this very flattened distribution that you see here, right? Now you've got more uncertainty. As you spread this distribution out and fatten those tails, you increase the uncertainty, okay? And so what we want to do is provide information that collapses that, right? This is the kurtosis of the distribution. We want to get that more peaked, right? That way we've got less uncertainty and we're closer to the categorical forecast, right? Which is something we know for sure. So now that's the first part, right? It's got to be relevant and correct. In order to do that, if it's relevant, maybe we don't change the shape of this distribution at all if the information is completely irrelevant, right? We haven't done anything to help ourselves to reduce our uncertainty and collapse this distribution. If the information is incorrect, right, particularly if it's specious, right, like we think it's correct but it's not, then we can move into, I think this thing, sorry, I have to do both. Then we could move a distribution that's normal into something that's more like this and broaden the uncertainty, right? Everybody sort of get this relationship with uncertainty and information, right? And then the second part is that information is not free, right? So you could think of this, this could be the distribution of wine, let's say wine prices, right? So average bottle of wine's here, and this is some $500 bottle of Bordeaux that's out here on the end, okay? So if you're a marine scientist and you like wine, you're going to be much more familiar with this part of the distribution of wine, right? This $500 bottle out here, this is rare. You don't have very much experience with that, maybe no experience with that. So it's very hard to understand what that experience might be like. And if you want to know what that experience is like, it's going to cost you, right? And it's the same thing with information, right? The more information that you want, especially in the offshore domain and in difficult areas, it costs you more and more, right? And so this is just another example of this, using sample size, right? So again, we have this kind of a distribution, right, with a lot of uncertainty out here, and then this would have the least amount of uncertainty like this. And this is framed in the context of sample size, right? So this sample size has 2,401, doesn't matter. This sample size down here has 96, right? So as you increase that sample size, you're collapsing the uncertainty, right, and becoming more certain about something. So you could, in the marine science realm, as it pertains to offshore wind, right, you can imagine you saw one of those lease blocks. We'll use physical oceanography for this demonstration. One of those lease blocks, you could put an ABCP right in the middle of that lease block, 1, right? And let's say that's going to cost you $1,000 to do that, right? And then you're going to extrapolate from there for the 10 kilometers, right? It's a square box, 10 kilometers on a side, right? A lot of uncertainty there. You've got 1 ABCP, but it costs you a lot less money. Or you can put 10, right? So now you've increased your cost quite a bit. Now you've got 10 of them out there, right? But you've decreased your uncertainty, right? And so this is the balance that's always being played in any kind of offshore endeavor, right? Okay, so just to summarize here, key role of marine scientists and industry is to acquire, process, and interpret data and convey the information so as to reduce uncertainty, which leads to a reduction in risk, which increases the quality of work and the profit. That leads to an enhanced ability to stay in business, gain market share. If you're into it, do R&D, right? And then it comes that equals more profits, more projects, and it starts itself over, right? So this is the cycle in industry. So the key point here, like I said earlier, is that marine scientists are in the information business and they're conveying this information, but to who? The engineer, right? The engineer's king. Any engineers in the audience? No? 1, 2, right? You're in the wrong room. You should be in business. The engineer is king, right? Engineer's king in industry. There's no doubt about it. There's some minor exceptions in exploration and hydrocarbon, right? There you're working usually for a geophysicist or a geology, but in every other instance you are working for an engineer. Offshore wind is entirely an engineering exercise, entirely, right? And so it makes sense that these would be the people that you report to, the people you work for, the people that use your information, right? And this is a quote I like from Nassim Taleb, right? There's a difference between knowing something and knowing how to do something, right? Well, engineers know how to do things by default, right? I mean, it's baked in the cake, right? That's what engineers do. I mean, the definition is almost, applying knowledge to some practical application, okay? So engineers, very practical skill set. They don't have this problem. Scientists, on the other hand, in industry, you may know a hell of a lot, right? You may know a hell of a lot about sea level. You may know all the mechanisms from a orbital forcing standpoint and the nonlinearities and all the math and how it all works and everything else, but who cares? The engineer, on the other hand, knows how to build a seawall, right? He knows how to build a jetty. He knows how to build erosional control structures, right? So it's taking this expansive knowledge base that you gather here, and then if you're in industry, how do you channel that into something that the engineer can use? Right? The engineer doesn't care about Milankovitch cycles. He doesn't care about these kinds of things, not at all, right? But there is some information that he does care about, right? So that he or she can construct whatever it is that they're doing. And this is very much the case in offshore wind, right? So just very quickly, I think it's relevant to point out often, sort of the reverse. At least my experience in academia, it was often the engineer that was working for the scientist, right? Scientists have the tenured positions, they typically have the grant money, and the engineer supports them. In industry, it's flipped around, right? You're almost always working for the engineer, and that's especially true in offshore wind. Okay, so working with and for engineers, right? So this is the mind of a scientist, which is usually a mess, right? There's all these graphs and curves and colors, and I mean, this is actually my bag, right? This is sequence stratigraphy, and I can't make sense of this. Maybe Stanley can. Right, but there's a whole bunch of information here. There's a sea level curve here, and there's all this jargon about falling stage systems tracks, and then there's stuff about grain size, and all to kind of describe what this depositional pattern means, right, and the geometry of this depositional pattern. Right, and this is a carbonate system, which is different than a siliciclastic system. Right, but here's the engineer. See this slope? Engineer doesn't care about any of this. What he or she cares about is when does it fail, right? When does, at what point does this get steep enough or unstable enough, or the conditions in the surrounding water column, right, or tectonics or seismics or something like this causes this to fail, right? Now it's still important. All this information is important, right? And this is something I deal with engineers, right? This is what they're thinking of. They got a force diagram in their head. They're just wondering, how does this fail? Or when does it fail? Right? But there's important information that, in this case, a geologist can deliver to the engineer. And that is a lot to do with the carbonate sedimentology there, right? If this slope in a carbonate system compared to another slope that engineers are usually more used to working in siliciclastic systems, this will stand up much longer at higher angles and withstand more due to cementation and other things like that, right? So there is information that the scientist has that can pass to the engineer. It's just distilling all of this into something that the engineer can plug into their equations and various softwares that they design things with. Okay, now I'll get to some wind farm stuff. Okay, so one of the biggest things in wind farms, of course, for marine scientists is what happens below the water. Right up here, doesn't matter too much. Well, the force gets imparted on the, so there is some relevancy there, but okay. Engineers think very much about design, right? And at a first cut, they need to focus the design. And this is where information from the marine scientists becomes very, very relevant in offshore wind, right? So in this case, the engineer is typically in Europe, right? And has never built a wind farm over here in the United States. And so at a minimum, I mean, he's not starting from scratch. They have a lot of operational designs to choose from, right? They have a template to sort of work from. But in order to focus that design or constrain that design, they need input from the marine scientists. So a first order input would be, how deep's the water, right? How deep is the water? Because depending on how deep that water is will dictate what kind of design they use, right? That would be a first order thing that they would need to know. And they would need to know marine science, or they would have to commission bathymetric surveys. We'll talk about those later, right? So furthermore, the subsurface conditions, hugely important, right? What the seabed is like, right? And so we'll get into more of this a bit later, but that information, right, going back to my previous slide, we're focusing the design, right? So we're taking this part, right, and we're narrowing it. Right? We're taking away the uncertainty, we're adding more information, and we're getting closer and closer to constraining that design. In this case, it's the wind turbine foundation and anchoring systems. Okay? That's hugely important. Right? This is a major thing that marine scientists do in offshore wind, is assist in providing the information to design the anchoring systems, everything below the water for the most part. Physical oceanography, you need to know the current regime quite well. You need to know the sediment transport regime quite well. All kinds of things, right? So we can constrain the design. Now this is where the real savings comes in though, right? If you're the engineer, engineers think a lot about safety factors or factors of safety. Okay, now this is a wide branch of engineering with some high-level mathematics that I don't understand, but this is the distillation of it is this, right? A safety factor of 1 fails at the design load. A safety factor of 2 fails at twice the design load, right? So if I design this table to withstand 1,000 kilograms, if I've got a safety factor of 1, I go 1 kilogram above 1,000 and it breaks. Safety factor of 2, it'll hold 2,000 kilograms, right? But it'll cost a hell of a lot more to build that table, okay? And so this, again, we come back to the information, right, and how that works. If we can know, right, with infinite certainty, if we have the categorical forecast, and let's say that we hypothetically could squeeze this Gaussian distribution into something with extreme kurtosis, right, where we knew that this table or that wind farm foundation would never take a stress more than X, whatever the hell it would be, okay? Then safety factor of 1, 1.25, and we're good, right? The less that we know, right, the fatter these tails are out in here. Now we've got to throw safety factors at it. This is huge in oil and gas, right? Huge in oil and gas. But, and the safety factors, it's not like there's like just one safety factor. It's safety factors on this, safety factors on that, safety factors on all the critical components of these pieces of infrastructure. So you can imagine if you went at this thing blind, right, or half blind, you're going to have to throw a tremendous safety factor on that, and that is going to drive your costs through the roof, right? You want the minimum safety factor that is effective, right? And then once you have some notion of that, it's going to take information to do that, right? We've got to collapse that distribution. We've got to get rid of these fat tails, get rid of the uncertainty. Then the engineer looks at the consequences of failure and the cost, like I said, right? So in some cases, if it breaks, it breaks. We're only going to go so far, right? Because there's no, they'll look at it, what's the probability of loss of life, what's the impact to the environment. If a cable breaks with non-essential information, who cares, right? They look at it. What's it going to cost us to go patch it versus what's it going to cost us to engineer it with a safety factor of 4, right? So does this make sense? So this is in large part where the marine scientist makes his money in engineering type things like offshore wind, is right here, is giving as much information as you can to that engineer about the physical environment that they're working in so that they can constrain the design, get the right design so it doesn't fail at some point, right? And then get that minimum safety factor. And the better data you have, the more information you have, the lower the safety factor can be, right? And the cheaper it is to build it, right? Because this is business, right? This is cutthroat. There's lots of competition, and the person that can build it better, faster, and cheaper, like any other business, wins. Okay, it goes a step further, right? So the engineers, we're talking about the design stage at this point, right? So the engineers are designing these things, right? They're designing, and then they're putting the safety factors and all the rest of it. But now somebody's got to build it, right? Somebody has to go and build this. So this is the next step. I'm skipping a lot of steps, but in the broadest sense, this is the next step, is you've got a contractor that's going to come out and build and install these kinds of things, right? Now you imagine, for example, well, before I go any further, so estimating, bidding, and contract risk. So the uncertainty translates to risk. We've covered that. And de-risking in industry translates into cost increases. So you can imagine if you're going to build a dock and you call up a guy to get an estimate to build a dock in the back of your house. And he says, well, how deep's the water? Well, I don't know. It's between 5 and 15 meters, Okay. What's the tidal variation? Well, I don't know. I'm not quite sure. It's 2 to 4 meters, right? What's the seabed like there? No idea. What kind of bid do you think you're going to get back, right? He's either not going to take the job, or he is going to give you an estimate that is hugely inflated because he or she has to cover their risk, right? Because they've got to come out there and they really don't know what they're up against. They don't know what they're going to encounter, right? So they mitigate for that uncertainty with cost, okay? So this, again, is hugely important role of marine scientists, right? Is to give as much information as they can to those engineers and others so that when these things go out for bid, they can get attractive bids, they can get accurate bids, right? And their projects can come in on budget. Does that make sense? And it's a nonlinear thing. I did this on purpose, you know. As this goes up, right, exponential increases in cost, right? They'll jack that cost up to cover their risks. Especially when, you know, you have some sense if you're a professor here what ship time costs with a weatherbird or something. Now you think about this operation, right? Something goes wrong out here and this thing sits idle for a week or a month, right? You rack it up big, fast. Okay, so sort of starting from the beginning, how do these things get developed, right? And so this is BOEM's perspective. BOEM is very much the Bureau of Ocean Energy Management. They're very much a part of this process, right? And so this is their sort of schematic about how this works. And so first is planning and analysis. This is on their end, right? This is BOEM, this is the feds. And I'll skip over a lot of this stuff, but you've seen this before, these polygons. These are the blocks, right? So this is borrowed from the oil and gas industry, where in some collaboration between the state and the federal government, they partition the continental shelf into, well, polygons here, lease blocks, right? In the context of hydrocarbon, oil companies would bid for the rights to come out here and explore this, right? Explore it for viable hydrocarbon reservoirs, and then they go on with permitting and other things to if they're eventually going to develop, you know, a viable reservoir out there. In the case of offshore wind, these blocks are available for lease through bidding by the developers of offshore wind. These are, you know, potential wind farms. These are places that the state has said you can build, right, if you meet our requirements, wind farms in these areas. And these are probably set up in a way so that this is New York City, so shipping lanes could come through here, right? So then we're leasing. So that's on the state side, is to get all this kind of thing set up here, right? Then you have the leasing. There may or may not be a competitive bid. That's an entirely different story. But at some point, somebody winds up with one of these leases. In this case, it was, I believe this is Statoil's lease here. And then it goes into site assessment, right? So site assessment is where the marine scientist becomes heavily involved at that point, is assessing this site, right? Assessing the geology, assessing the biology, assessing the physical oceanography, assessing the meteorological conditions, the whole 9 yards, right? And then it goes into construction and operation. At this point, there's a lot less. Still marine science professionals involved here, but a lot less. This is the real action from a marine science standpoint, is in the site assessment. Okay, and so these are the types of activities that involve marine science. And so the first order of business, this is from an industry standpoint. First order of business is a desktop study. So this is analogous to your literature review that you would do before a dissertation or a thesis, or before, you know, a grant proposal, something like this. This is amassing as much information as you can about the area that you intend to work in, right? And once you've done that, then you would move into the permitting and consent, right? So you would get permission from the state and federal level, even townships sometimes, to go out and conduct your investigation in this area, right? These are acoustic investigations a lot, seismic and otherwise, so there's all kinds of implications to that. There's shipping lanes, there's all the things. So you need permission to be out there doing what you're doing. You need the permits to do it, right? Once that's in place, then you'd move into what's called a reconnaissance level survey, right? Every company does this slightly different, so I'm generalizing, but you get the picture. And so the reconnaissance level survey would be your whole block, right? So you've won this block, let's say. You now have permission to go out here and characterize the site so that you can potentially develop it for wind energy in the future. So you come out here and you would do a a big line spacing, so think of it as coarse sampling, if you will, and get a sense of what the geology and the oceanography is like across the whole block, right? Then you would come back and you would process, interpret all that data, you would assess it, and then you'd come back to the site level, right? So they probably surveyed most of this block, if not all this block. And you see this is what they chose, right? And I know really nothing about this particular survey, but I can tell you right now, the reason they chose this is just there were no hazards, I would bet you. There was nothing in this block that was a no-go, right, from a foundational standpoint or the cables or anything else. So what they did is they took the engineering solution, right, and they took the closest point to the beach, right, because it's cheaper. The water's shallower, right, so it's easier to work in. Every time you've got all kinds of vessels that make this transit, right, that's cheaper. Cables, now they're shorter to bring it onto the grid. So they probably didn't see any kind of hazards there, and they chose to develop this part of the block. Right, so that would be the site level survey. So then they would come in here, tighten up their line spacings, more instrumentation on the bottom, perhaps mooring arrays. They would amass a better, tighter sampling set of the oceanography and the geology here, right? Then at some point, at that point, they'd have their arrays too. How are they going to, from an engineering standpoint, put all of the wind turbines, right, the WTGs, in what type of geometrical pattern are they going to do? And then they go into the micrositing, right? So they'll have it down to about 100 square meters on either side, and then they go in and actually shoot 3D seismics and do very, very detailed site assessments of these little tiny blocks so that they can move a foundation a few meters this way, a few meters that way, right, and get the optimum position. And then, of course, there's surveys that are related to all the inter-arrays and all the cable routes, right? So you've got to bring that power off of the block, and you have to bring it onto the grid, right? And then all those individual wind farms that you or WTGs that you saw, there's an inter-array cable system that takes that power and focuses into a single point, converts it over to DC from AC, and takes it to the beach, right? So that's the way that it works. So what are the relevant technical fields from marine science that goes into this kind of operation that I've been describing? Geodesy, geophysical survey. I'll look at each one of these individually. Geodesy, geophysical survey, hydrographic survey, met-ocean. This is an industry term, which is meteorology and oceanography, right? So this is the physical oceanography side of it right here. PSO, these are the biologists for the most part. These are protected species observers. They do passive acoustic monitoring, so it's not just being out there with binoculars. They actually do some pretty sophisticated stuff. And I thought about putting this under technical fields, but I go ahead and give them a pass. The archaeologists, they come into this as well. They're actually a big part of this is archaeological investigations, looking for shipwrecks and all kinds of what they call cultural artifacts on the seabed that might prevent construction or you'd have to move or something like this. Right, so like we talked about before, in the interest of time, I won't get into much of this, but a lot of this is focused focused on foundation design and installation, and these are the various kinds, right? These are, you can see, most of the time it's a monopile. Just think of a pylon, right? It's a little more sophisticated than that, but it's essentially what it is. They've got gravity-based systems, right, that just sit like a pedestal on the bottom. Tripods, these kinds of jacketed ones. This is an oil and gas thing, sort of like a rig would have jackets on the legs. Tri-piles, suction buckets, if you're familiar with that from an oil and gas standpoint. And this is what the operation looks like. Another key point, one of the reasons I have this slide here, this is a jack-up rig. So this is technology that's born out of oil and gas industries. So the legs are jacked up here. And so now it's a vessel. Right? And so it can move, right? It's self-propelled, it can move, it stops where it wants to be, and then it jacks itself up, right? It climbs, ratchets itself up, and this would be the equivalent of the water depth that it could operate in. So it jacks up off the seabed. But this operation requires a lot of input from marine scientists. Because you can imagine if one of these legs, we call it a punch through, if one of these legs punches through, and that thing tips, right, game over. So very important. A lot of work goes into understanding the geology related or the environment before they do something like this. right? Then this is just an example of the inter-cable arrays, right? So this is the London array, as you might guess, off of London. These are the WTGs, and this is the complexity of those inter-arrays that I was talking about. So you can see they're getting consolidated here and here, and then they would come in as direct current. It'd be AC out here, transformed here, and then come in DC. Okay, so back to the technical fields, geodesy, right? We can't do anything without geodesy in any kind of offshore construction project or oil and gas, right? This is what underpins all of our coordinate systems. It's what underpins our projections, right, which is the way that we display our coordinate systems. Datums, that's all of our vertical positioning, hugely important from a construction standpoint, also from the standpoint of correcting bathymetry data. We're referencing it to mean sea level or some other datum. And then, of course, the whole GPS system. These are the sites that make up the ITRF system, right, International Terrestrial Reference Frame, very complex system of positioning, but it gets better and better, and the GPS positioning offshore now is 10 centimeters or less in the horizontal, so very tight positioning. Okay, acoustics, right? Acoustics and the principles of acoustics, super important, right? Super important for any marine scientist to understand, and because they underpin almost all of geophysical and hydrographic survey. And especially for offshore wind, that we don't do much gravity and some of the other things that oil and gas do, right? So I'm just going to go over, I'm going to skip a whole lot of physics and just go over some key principles here as we look at some data sets, just to give you some reference, right? So the concept that we make great use of this is massively oversimplified, is two-way travel time, right? So we're transmitting sound through the ocean. We know what time the sound left the transducer very precisely, and we know what time it came back, right? So we have a duration, and then we measure very carefully the velocity of the water in the water column, right? An integrated profile through the water column. And so once we have that information, we can convert it into a distance, right, into meters. And this is the foundation of bathymetry, it's the foundation of seismic, and from that point what we're doing is we're manipulating the frequencies, right? And these are some key principles to understand, and the relationship between frequency and resolution. As frequency goes up, you raise your frequency, your resolution comes up. You decrease your frequency and you increase your penetration, right? So now you see deeper into the seabed. And then if you increase your frequency, you decrease, that should be the other way around. Increase frequency, you increase your attenuation, right? So Multibeam Echosounder, this is the workhorse of the industry for bathymetry. This is highly variable for offshore wind farms. It's usually about 300 kilohertz, right? So those are kilohertz. That's high frequency insonification of the seabed. You don't want any penetration in this particular application. And this is what the data looks like. This is spectacular data. I just pulled this off of Keris's website, right? But anybody know what this is? Geologic interpretation? I'm guessing myself, but I have a pretty good idea of what I think I'm looking at there. No? Stanley?
It's Europe someplace.
Well, those are beds, right? So those were horizontal beds that have now been thrust up or tilted up like this. So they were originally like that. Now we're looking at them like that. So we're looking into the strata, and then of course we have some faults there in here. The point I'm here, it's not to do a geology lesson, but just to give you an idea of how spectacular this data is.
Where is it?
I don't know. No idea.
Salto.
No, it's not a salt dome. That's strata. That's for sure. That's sedimentary rock.
And there's sufficient faults to break the seafloor.
Yeah. Those are emergent faults there going this way, but those are beds. I'm nearly certain of it that have come up. So this just gives you another piece of data from Multibeam Echosounder, giving you an idea of sediment transport, which is hugely important in the offshore wind industry. Scour, as you might imagine, is a real problem with these things, right? They tend to be in areas where there's a lot of energy in the water, right? There's a lot of wind. Wind means swell, wind means current, so there's a tremendous amount of scour around the bases of these. It's a real problem. And so this kind of information is valuable, right? We can see that there's sediment transport ongoing. You've got some big sand waves here. You've got some superimposed stuff here. So useful information for the engineers. Also very important from the cabling standpoint, right? Side scan sonar. What time we got to wrap up here, Alan? At 4:30?
Well, 10 minutes.
Another 10 minutes, all right. Side scan sonar, another instrument, right? High frequency. I'll move quickly here. This is what this looks like, right? Again, this is information for the engineer to understand the seabed. Again, we can see rocks. If there's rock outcrops here, we can get some information about the texture of the sediment sites. We can infer some things about grain size, some things about hardness, softness, sediment transport that we see here. It's useful for picking up debris. This might be a length of rope or wire or something like this that's on the seabed, so it has dual purpose from a geology standpoint as well as a obstacles and debris standpoint, man-made objects. Sub-bottom profiler, you see the frequency's coming down, right? We were at the hundreds of kilohertz when we started, right? Up to 900 kilohertz with the side scan, so now we've come down to 5 to 25 kilohertz, so based on the things I was saying earlier, now we're going to get penetration. We'll see into the seabed, right? So these are a couple examples of sub-bottom profiler data, right? So getting a very high resolution look at the at the stratigraphy here in the seabed, or rather below the seabed, right? Again, hugely informative if you're going, and we'll get to this part, if you're going to try to bury cables here, right, or if you're going to put a foundation here or anything like that, this information is very, very valuable to understand what's in the subsurface. And I would bet this is probably gas in here. That would be my guess, that this is shallow gas. This is the gas front there. Okay, this is the workhorse of offshore wind development, and this is 2D and 3D ultra high resolution seismic. So the frequencies are getting lower. We're into hertz now. Well, that would be 5 kilohertz, but nonetheless, this is 250 hertz. We're getting greater than 100 meters penetration, right? So this is New Jersey, right? This is the seabed in New Jersey, right? And these are buried channels, super high resolution, really, really good data. This is the continental shelf off of New Jersey. This is 20 meters right here, right? And these are expanded views of these channel sequences that you see here. All right, so this is off of Massachusetts, and this is glaciotectonics right here. So you can see this was thrust. This has been thrust here. This has been thrust here. This has been thrust here. These are called piggyback thrusts, right? If you look into a glacial geology book, you'll see some examples of these in outcrop. But this has been thrust one on top of the other. This is super important information for the engineer, right? Because this has a very different load and stress history than sediments that haven't been tectonized, right? These have been moved, they've been disturbed, okay? So they have a very different geomechanical stratigraphy than things that are in their original depositional attitude and configuration, right? This would be a transgressive ravinement coming right through here, and this would be the Holocene sitting right here. This would be the low stand, obviously, when the glaciers were out there on the shelf creating this kind of deformation here. Gas. Right, this is what gas looks like in seismic data. That's an important thing to know when you're drilling and doing foundation work and things like this. You get a sense of where this technology is today. This is incredible resolution here, angular unconformity here, all this fine bedding. Oh shit, I didn't even. This is 3D, right? This is 3D data here. So this is the microsiding that I was talking about. So they've done the reconnaissance level, the site level, and now they're all the way down, and they want to put a wind turbine here. They want to put a wind turbine here. So now they actually come in and do ultra high resolution 3D seismic data. So this is a time slice from 3D seismic data. I'm guessing it's non-migrated based on what I see here, right? But this is that. So here's the 2D profile version. This is a migrated section, right? So if you're a geophysicist here, you understand what I'm saying. This has been migrated, right? So the hyperbolic reflections have been collapsed back in. The energy's been collapsed back to correct the geometry. These are boulders, right? Big ones, probably in the North Sea, right? So this is a major hazard if you're going to put a foundation there or a suction pile or something like that. So you can identify them here in 2D, and when you have 3D data, here it is. Right, so then you can say, okay, yeah, we'll put the foundation here. We'll move it this way. We'll move it that way. So that kind of info, this is hugely expensive to do this, these three, but worth it, right? Worth it because you can avoid things like this, a couple of days shutdown on one of those rigs that you saw, right, easily would cost more than one of these surveys, okay? And this is the magnetometer. I put this last because it's not an acoustic thing. We were talking about acoustics, but this is also a very useful tool in offshore wind farm construction. And it will respond to the geology signal, I guess you would say, but we use it mostly for debris, right? Finding ferrous objects. It actually doesn't respond. It measures the Earth's field, right? And if there is something ferrous there, that is deforming the field. So it's not a metal detector per se. It is measuring the ambient magnetic field. That magnetic field is deflected based on the presence of ferrous objects, and then it's measuring the field, right? This is magnetometer, which is two magnetometers, and you think here like stereo, right? So this one, there's no directionality to this. It just takes a hit like this. This one, due to the principle like in stereo, you can now determine directionality. You can go different directions. You can grid this data, and you can come up with this. This is very valuable, particularly in Europe, given all the wars they've had, for UXO. This is the workhorse for UXO. UXO is unexploded ordnance. It's not too much of a problem here, but it's a big problem in Europe. And they routinely go out and plenty of bombs, plenty of things that are unexploded. They have teams that go out and attach other explosives that up, and right, so it's a big part of the game over there, not so much here. And then archaeology, shipwrecks, and things like that. Yeah, okay, so that's basically the talk, and this happened, I think, when did this hit the news, Chris?
Last week.
Last week, right? So I had already put this thing together, and then this popped up in the news. This is Block Island, right? Block Island, that's our 5 wind turbines, okay? And so what happened here, at least according to the news, if you can trust that, what happened here was, remember we talked about the cable that takes the power to the beach, DC cable, okay? So they did geophysics, they did surveys to support that operation, and they determined, they said, look, we'll plow it, all right? And what that means is they have a big plow. Think 1800s behind the cow kind of a thing, but this is pulled behind a boat, and it's 300 times bigger, right? Something like this. And so it plows along on the seabed, and the cable lays right underneath it. Okay, so think of it like that. But so that's what they wanted to do, which is much cheaper than what's called directional drilling, which is to actually drill down and laterally drill through the subsurface like this. So they went with the cheaper option based on all their data. Now, I haven't seen the data, but I'm about to. So they made this decision, we'll plow. Well, at some point, the plow hit subsurface boulders, right? So now it can't plow at its normal depth. It hits those boulders, and now it comes up. This is a glacial environment. This is off of Block Island, which is a part of a terminal moraine. So there's boulders there and cobbles. The plow hits that, and it comes up. So now they can no longer plow to the depth that they would like to, whatever the hell that is, 5, 6 meters, I don't know. What would it be, Eric? 3 meters?
Yeah, about that.
About 3 meters, right? So now they come up, let's say they're a meter. But they cover it in and so on, and they go on their merry way. Well, over time, now those cables are exposed, right? They weren't buried deep enough. They weren't buried to code, you could say. And now through currents and tides or whatnot, storms, the cables are now emergent, right? They're open to the seabed, and so now they'll probably have to shut this thing down. Imagine this: they're going to shut this thing down. They're going to go out. I mean, it is a disaster for them, right? I'm certain it will go into the millions. So you see what I mean? This is a perfect example of using information, having the right information, believing in the This is the role of marine science and industry, right? The good thing about being a marine scientist is a bunch of marine scientists made money on the front end of that, and now a lot of them are going to make money on the back end of that, right? This is the time when you don't want to be the engineer, right? And I'm going to take 2 more minutes. This is more information, whatever. this is one thing for the students, because I did this, when Al asked me to come, I said, yeah, I'll come back, but I'd rather talk to the students, because I wish, I had some insight. I had spent 5 years in industry before I came here, right? But translatable skills, right? While you're here at the university, there's the new school and the old school as I see it. The new school, right? If you want to be employable, and I talked to a lot of, I guess, colleagues, people that I went to school with when I was here, and they can't find jobs, right? Or they can't find the jobs that they want. It seems crazy to me because I know the people and they're skilled. But coding, right? Computer code, hugely important, right? If you can do that and be good at that, you'll always be employable. GIS, right? This is ARC, these various softwares, hugely important across all of industry, right? And then data analysis, right? Quantitative data analysis, right? Math. That's hugely important. The courses that when I was here was Don Chambers, I think. Great course, right? Because it translates across everything. It doesn't matter what you do. It's always the same. And then the old school, right? Writing skills, that's going to hell, right? I'm not that old, but I make a good living because I can write, right? And a lot of people that are coming out of school, they just can't write correctly, right? Or they can't write to a level that industry is used to seeing, okay? And then communication skills, the ability to talk, right? The ability to talk and communicate, right? Super, super important. Not so important in academia, right? I've watched many, many academics stand up here when I was in your shoes, and I didn't know what the hell they were saying, right? I'm not saying that I'm the most polished speaker, but I was lost, right? I was lost or didn't care, like Al was saying, right? I'm sure you were, the hell is this? So being able to communicate, connect with people, convey an idea, massively important in industry. And this is the other thing that I made this up, talking to a couple people in my, I think there needs to be a paradigm reversal in the way that especially PhDs think when they come out of school. I talk to colleagues of mine, friends of mine, get their PhD, can't get a job, right? And so this is their mentality. So as an undergraduate, right, I use geology because it's closest to me, right? So now I'm a geologist, right? It's broad. This is the academic. I keep using this thing, it doesn't work. This is the academic mindset, right? You're a geologist as an undergrad, right? Super broad, super broad. As you go to grad school, you start to drive this down. Now you're a carbonate marine geologist, right? And then by the time you've got your PhD, you're an expert in the dolomitization process of the Bahamian Miocene limestone. Fair enough. How many jobs are out there for that? Maybe one, right? Maybe one, okay? In an oil company in their R&D department, okay? Maybe one. But that job, right, that's been advertised all over the world because these are global companies. Energy companies are global companies. So good luck. Good luck competing for that, right? And then good luck getting paid what you want to get paid to company, right? This is what I would suggest, right? When you start out here, really, it's narrow. You don't know that much, right? And you build on this skill set through your master's degree, right? And you're broadening, right? But you never forget what you did back here. And you build and build and build and build and build, right? Until you finally come out with your PhD. And yes, this is what you did your PhD on, just like I did my PhD on the loop current. I haven't said loop current since the last time I was in this room defending my dissertation. It's true. I think this is the first time I've said loop current, right? In business, right, you have to sell yourself this way, right? You don't sell yourself as that. You sell yourself as this, as a broadly skilled, versatile scientist, right? And this is one of my favorite characters in history. This is Miyamoto Musashi, right? This is the best samurai, as far as we know, that ever lived in Japan. You can look him up. Real guy. And he says, if you know the way broadly, you will see it in all things, right? And so that's what I'll leave you with, right? When you leave here is to know the way broadly, right? And then be able to see it in all things, right? And then you'll be widely employable. Yeah, that's all I got. Thanks for coming.